so you want to see Bernoulli's principle? Okay. Bernoulli's principle, first of all, you need to know that it's based on the conservation of energy. And that's in contrast to the equation of continuity, which is based on the conservation of matter. Okay, so if you look back at the old test, you'll see questions like that. Which of these is based on the conservation of matter? Which of these based on conservation of energy? In general, for all those principles, Archimedes, Bernoulli's, Pascal's, and the continuity equation, you sort of need to know in words what those are. Okay? But Bernoulli's equation, based on the conservation of energy, and it says that P1 plus 1 half rho V1 squared. You have another term on your equation sheet that's plus rho GH1, but we're not going to worry about that. So we'll just leave that out because our height is going to stay the same. Is equal to P2 plus 1 half rho V2 squared. And then again, you have this other term, rho GH2, but we're not worrying about that. Because that would only apply if you had a fluid that changed height. So that this would be H2 and this would be H1, but we're not going to have that. It'll just be in a straight pipe, so it's going to have the same height. So those terms are going to cancel one another out. Right, and the way you'll see this is I'll say you have a certain gas or a certain fluid that has a pressure. Say the pressure is 1,000 pascals. It's flowing at a certain speed, say 5 meters per second, and in one part of the pipe, and then in the next part of the pipe, it's flowing at a speed with 10 meters per second, and I want to know what is the new pressure. Okay, so you'd have fluid in a pipe, water, say for example, it has a certain pressure and speed in one part of the pipe, and then in the next part of the pipe, it has a certain pressure and speed. So like for example here, this would be a scenario where I have a pipe that gets smaller, so that the speed over here is 10 meters per second, 5 meters per second. Yeah, so what's going to happen to the pressure over here when the speed goes up? Right, it gets smaller. So if V increases, P has to decrease because the sum of these has to stay the same because of the conservation of energy. The energy always stays the same. So if V goes up, P goes down. So I could already say that this P has to be less than 1,000 pascals. All right? But I can calculate that, and you'll need to calculate it. There is a question like this on the test where I say P1, that's 1,000 pascals, plus 1 half of rho, let's say it's water, so rho is 1,000 kilograms per cubic meter, times V1 squared, that's 5 meters per second, squared. But that's equal to P2 plus 1 half of 1,000 times 10 squared. And then I would solve for P2. So this would be what, 500 times 25. How's it going? So, whatever P2 is, I don't know. It is what it is. Okay? Y'all can do that okay? But you will have a problem that looks like that, where you have to solve for the pressure from Bernoulli's principle, or the velocity. No, it'll be fairly straightforward. It'll be stated up clearly. The pressure is here, the speed is here, and then in the second part, the pressure is or the speed is, and then you have to solve for either the P2 or the V2 in the second part. Okay? You have to solve for P2 actually. It's a little easier to solve for. Alrighty? Y'all could do that? Do you want to go on into chapter 10 or do you have more questions about chapter 9? Okay. All right. So let's look at chapter 10. We have a few things in chapter 10. We have linear expansion. When something heats up, it gets bigger. We have ideal gas law, which we haven't gotten to yet, but you probably had the ideal gas law. It says that PV equals nRT. We'll do some problems like that. You got to watch your units with the ideal gas law because your units are sometimes funky. What else we have in chapter 10? There's not that much really. Oh, temperature scales. And sort of basic ideas about thermal equilibrium, what that means. Uh, yeah, that's it. Isn't that all? You have another topic in that chapter? Yeah, ideal gas law. Blah, blah, blah. Yeah, I guess that's it. Mm-hmm. Chapter's not very long. Yeah, so linear expansion. Uh, this, if you have a material that you heat up, we can figure out how much it expands. So let's say that I have a steel bar that is 1 meter long. I heat it up by a change in temperature equal to say 100 degrees Celsius. And I want to know what's the new length of the bar. What is the new length? A couple things you need to look out for. That should be TH. Sometimes they'll ask for the new length, and sometimes they'll ask for what is the change in length. So when you're using this linear expansion equation, this delta L, this isn't the new length. This is how much is it increased in length. So for example here, if I wanted to know what is delta L, I would say alpha, which for steel is 11 times 10 to the minus 6. Let me show you where that is. There's a lot of stuff on your equation sheet. And like I made out the test earlier today, and when I worked through it, I found that I had to go back to that equation sheet a lot because I'm looking at tables, I'm looking at equations, so you'll need to do the same. Just make sure that you print it out and that you're familiar with what's on there. And again, the test is 28 questions long. It's sort of equally from the chapters, although the last chapter there's not as much. Let's see, so for steel, yeah, 11 times 10 to the minus 6, it's right here. That's my linear expansion coefficient. L naught is the original length, that's 1.0 meters. And my delta T is my change in temperature. So I might give you the initial temperature and the final temperature. You'll just need to take the difference between those two. Right. So, but here I just give you 100 degrees Celsius. So that is, well, that's 11 times 10 to the minus 4, right? So my new length is going to be 1 plus 0.0011 meters, because that's 11 times 10 to the minus 4. So my new length is 1.0011 meters. The good news about this chapter is there's, the questions are, they don't really require a process. They just sort of require that you know how the equation works and that you know what the numbers are and that you get the units right. Although in this case, the units sort of are as they're stated. 1, this was the original length because I want to know what is the new length. I have this 1 meter bar. I heat it up. It gets bigger by 0.0011 meters. And so the new length is the original length plus that amount that it got bigger by. Okay? So this was its original length, L naught. This is its change in length, 1.1 millimeters or 0.0011 meters. And then this is its new length. It's this much, it's this new size. Yeah, 1 meter is L naught. That's the L naught is the original length. So this bar was 1 meter long. I heated it up, and it got this much bigger. I add this much to the original length. They don't multiply it. All right. I mean, you had to multiply it here, L naught times delta T times alpha, in order to figure out. Right. Be careful on that. Make sure you read the question. Sometimes it'll say, how much does it expand? And sometimes it'll say, what is the new length? I don't remember what I did. let's look at an old test and see. Um, you had a bunch of homework problems, or not a bunch, but you had several homework problems. Uh, so like, for example, let's look at this one. This one's probably a little more complicated than you'll need, but let's just take a look at it anyway. So here I have a brass sleeve. It's to be shrink fitted over a tooth whose average diameter is 1.5 centimeters at 30 degrees Celsius. The diameter of the sleeve is 1.498 at 30 degrees Celsius. So that sleeve won't fit onto the tooth because it's too small. So you have to heat it up so that it'll slip over the tooth. You want to heat it up so that this will become 1.500. So what you want is your delta L to be 0.002 meters. You follow what I did there? Because I want it to get bigger by 0.002 meters to go from 1.498 to 1.500, and then it'll fit over that tooth. You have a homework question similar to this, by the way. And then I know my coefficient. I give it here, but on the test, on your test for next week, you don't have these on the test. You have to look on the table. So sometimes, be careful that, gosh, I'm missing some key information. Make sure you go back and remember what's on those tables. I would just go ahead and print out that equation sheet today and just put it on your refrigerator, and you can sort of look at it when you pass by, just to be familiar with it. Degrees Celsius minus 1. Um, I want to know what is my delta T. And L naught is that 1.498. So now I say delta L equals alpha L naught delta T. And I solve for delta T, which is delta L over alpha L naught. Delta L is 0.002 over alpha, which is 19 times 10 to the minus 6. And then divide by L naught, which is, L naught, which is 1.498. I get 70 degrees. So delta T is 70 degrees, but be careful. I mean, it's not, C is not the answer because this is a change in temperature, not the actual temperature. I'm looking for the actual temperature. Gosh, what did it start at? Right, it started at 30 degrees Celsius, so my new temperature is going to be 100 degrees Celsius. I have to heat it up. I have to change the temperature by 70 degrees in order to get it to get bigger by that amount. Maybe something like that. I actually think that you're, oh no, that's probably a pretty good difficulty. And you have a homework problem similar to that too. Okay? Y'all could do that? Gonna be what now? Tricked. Right, yeah. But yeah, you do have to be familiar with the equation and what each of the values means. And that'll come with practice. Do each type of problem 2 or 3 times. Make sure you sort of understand the basic idea behind them, and then I think you'll be okay. All right? All right, so that's a good linear expansion problem and a good example. Uh, Also remember, think about when something heats up, it gets bigger. All right, that's the basic idea. And we had some problems in the concept test that were related to that. When something heats up, it gets bigger. And then also things based on their coefficient of linear expansion, they will heat up at different amounts. So for example, if I heat up copper and aluminum by the same temperature, the aluminum is going to increase a greater amount, right? Because it has a higher coefficient of linear expansion. That means it gets bigger faster. Okay? All right, so you have one of those. You'll also have an ideal gas law problem. We'll look at this one right here in just a second. But the ideal gas law, the hard thing about the ideal gas law is just make sure that you got your units right. Okay, so the ideal gas law is this. PV, that's pressure and volume, is equal to N times R times T. All right, P, everything needs to be in SI units for this. Everything has to be in SI units. but often they're not given in SI units. So make sure that you're clear on what the values are. P is in pascals, V is in cubic meters, although often the volume is given in liters, which isn't an SI unit, but I'll show you how to convert that. N is in number of moles. R is in, what is it, joules per mole Kelvin, isn't that right? I think that's right. It's on your equation sheet. Where is it? R, yeah, joules per mole Kelvin. Right, that's your gas constant. And then T has to be in Kelvin. So things you want to watch out for is often T is given in degrees Celsius. Sometimes volume is given in liters. Pressure is often given in atmospheres. You just got to make sure that you convert all those to the right unit. So say, for example, I give you a problem where the pressure is 1.2 atmospheres. The volume is, say, 2 liters, and the temperature is 100 degrees Celsius. I'll need to convert all those things. Now, I try not to give too many meaningless conversions, like just busy work, but on these things, these are sort of the common units that you have. But in order for to use the ideal gas law, at least when you're using an R here, this joule per mole Kelvin, you need to convert them all to SI units. All right? So 1.2 atmospheres, what is that in pascals? How many pascals are in an atmosphere? Right, 1 times 10 to the fifth. If you forget, that's on your equation sheet, but it's 1 times 10 to the fifth, so this is 1.2 times 10 to the fifth pascals. Okay? Liters, you don't know this right off. In fact, I don't even remember. Y'all might know this. How many cubic meters are in a liter? You forgot? uh, 0.001, right? I'll provide you with that if you need it. So, but it's 0.001. So that means that this would be 0.002 cubic meters. But I'll provide you with that if you need that conversion factor. Okay. In fact, you do need it, and I do give it to you in the problem. Okay. But make sure that you're aware of this. And then if I want to convert 100 degrees Celsius to Kelvin, you can go back to your equation sheet. If you want to convert your Celsius to Kelvin, if I have Celsius, I just add 273 to it to get Kelvin. So this is going to equal to 373 Kelvin. Is that right? I did that right. Okay. Yeah. And then I can do all these things. Now I can apply the ideal gas law. I say P, which is 1.2 times 10 to the fifth, times V, which is 0.002, equals N. I guess I'm solving for N here. I didn't give you N. Times 8.314 times T, which is 373. And then I'd solve for N. Now N is, you'll have this in the right unit. What is the unit for N? Do y'all remember from chemistry? Okay, it's the number of moles. Yeah. Of a gas. And of course, a mole is just a certain number of gas particles, that Avogadro's number or whatever. Okay? I remember this a little bit from chemistry. Y'all should have had this in chemistry. Okay, but the big thing in this is just getting the units right. You can also have some conceptual questions where I say, well, if I hold the temperature constant and I change the pressure, what's going to happen to V? Right, so if I change P by, say, a factor of 2, that means V has to go down by a factor of 2. We'll do this in class tomorrow. We have some questions that are related to this. That's really it. And you will have both of those type of problems. One where you have to solve for one of those quantities, and the big thing is just getting the units right. And then also one that asks you, if I change one variable, what happens to the other variable? All right, and 3 of them will be held constant, or really, there are only 4 variables, so 2 of them will be held constant. I change one, what happens to the other? Well, then, well, you can't really answer those questions if you have three variables that are changing. You have to only have two that are changing. Now, if your temperature changed, or if your temperature went up, then this quantity multiplied would also have to go up. The pressure times the volume. But let's say that I tell you the amount of the gas is constant. And let's say the volume of the gas is constant. If T goes up by a factor of 2, what happens to the pressure? It also has to go up by a factor of 2, right? However, what if T is constant, but P and V are both changing? If P goes up by a factor of 2, what happens to the volume? That it goes down by a factor of 2 or 1/2. All right, we'll see some questions like that tomorrow in the concept test. All right, so that's the ideal gas law. We did linear expansion. Um, what else did we say? And then temperature scales. So make sure you know those basic temperatures. So for example, 20 degrees Celsius is approximately 70 degrees Fahrenheit. Although you have those equations that allow you to convert between Celsius and Fahrenheit. Also know what they're based on. Remember that the Celsius scale is based on the freezing point and the boiling point of water. That's also true for the Fahrenheit scale, but the Kelvin scale, on the other hand, is based on absolute zero and the triple point of water, which is that point where you have water in all three phases all at once. The triple point of water occurs just slightly above 0 degrees, like 0.01. You look very sheepish. Come on in. That's okay. All right. Um, so you need to know those temperature scales, how to convert back and forth between them. But those equations are here, how to go from Celsius to Kelvin, and how to go from Fahrenheit to centigrade or Celsius, and vice versa. Okay? You okay on the temperature scales? I'm trying to think what else I could possibly ask. I think that's about it. What they're based on, what temperature scales, like what degree is bigger, Celsius, Kelvin, or Fahrenheit. We had that in class the other day. Which is it? Which is biggest? The Celsius and the Kelvin, they're the same size, right? Um, okay. Well, I want to work some other problems. That's all chapter 10. You want to dwell on chapter 10 for a little bit and look at some other problems on old test? What's what now? Okay, yeah, so the Celsius temperature, I always forget if it's plus or minus. I have to look back. The Celsius temperature is this Kelvin minus 273. So the Celsius and the Kelvin scales, they're the same size scale, the same size degree. They're just offset by 273 degrees, right? So if I want to convert one to the other, like if I have Kelvin and I want to convert it to Celsius, I would just subtract 273. So like for example, 0 Kelvin, which is absolute zero, is equal to minus 273 degrees Celsius. That is the absolute zero temperature is minus 273. Let's look at some questions regarding these topics. Okay, that way I am recording, right? Yeah. All right. So these are very good. Let's. You can look at this. Have you ever seen this question distribution? It's on the. It's always been there. It's at the top of your exam. Yeah. It's a little out of date. I didn't do last year. I'm sorry. All right, let's do '09. Looks like I had 10 questions. Yeah, we don't always get this far in this fall semester. One of the reasons is just y'all are awesome, right? But the other reason is just that often we have hurricanes or we have this or that, and this semester we've had a nice uninterrupted semester. So that's really the main reason why we've gotten so far. And now we're, finishing a couple days early. Yeah, it's a mess because, we gotta, everything's on Moodle, and it's like you try to sort of track along at the same pace, but you don't really. So you lose a little ground. Yeah, you just sort of try to be understanding. So let's look at exam 5 of 2013. Okay, make sure y'all are up on chapter 9. There's a lot from chapter 9 too. And basically every topic is on the test. All right, there are one or two questions from every topic. Andreas, I told him there are 28 questions. Okay, so here's one, for example, about the temperature scales. The Kelvin temperature scale is based in part on which of these temperatures? Which is it? Freezing point of water, freezing point of hydrogen? Right. Right, and absolute zero, right. So just know what those scales are based on. If it said, by the way, the Celsius temperature scale, it would be A, right? Or if it was Fahrenheit, it would also be A. Yeah, but boiling point's not on there. So yeah. 88 degrees Fahrenheit is how many degrees Celsius of these four? Without calculating it, just look at the numbers. 31, right. So 22 degrees Celsius is room temperature. A little hotter than that is about 30 degrees Celsius. Um, let's see, which of these can you use to measure temperature? Remember we gave a big long list of things that you can use to measure temperature? All of these, right. So uh, this is a constant volume, constant pressure thermometer, I think it's called. I forget what it's called. Anyway, length of a solid, that's like in your thermostat. The color of a glowing object, that's like a star. All of those you can use to measure the temperature. You won't see anything like number 22, molar masses. We just see ideal gas law. This is a good, let's see, we'll come back to, there's not much temperature stuff here. That was really it. But it's a good indication of what you'll see on the exam. The exam will be very similar to this. No, no, this is fall 13. What were you asking? Oh, fall 2013, let's see. No, this just covers 8 and 9. Or 9 and 10, rather. Yours is on 8, 9, and 10, right? Um, let's see what else. I mean, let's look at 2009. Okay, here's one. We did this one earlier, or one very similar to it. This is a lot like the tooth problem. You okay with that? Yeah? Okay. This is ideal gas. This is an ideal gas law, so you'd say PV equals nRT. And then you would solve for, oh, is that okay? It's not broken, is it? Okay. All right. Determine the number of molecules. You'd solve for N PV over RT. And then in this particular problem, you have to take an extra step and multiply it times Avogadro's number. You're not going to have to do that. But to find the number of moles, you would take the pressure. Remember watching your units. Atmospheric pressure is 1 times 10 to the 5th pascals. Everything needs to be in SI units. The volume here is given in cubic meters, so that's good. So it's 1 cubic meter. R is 8.314. That's that gas constant. It's on your equation sheet. And then 10 degrees Celsius is 283 Kelvin. Thank you. And then once you do that, you get the number of moles of gas that it is. Okay? Nothing more complicated than that. That's really it for the ideal gas law. Y'all can do that, okay? Just watch your units. That's where students are going to mess up, is the units. Let's see, the SI unit for temperature. Oh, we did this one. We did this one too. How about this one? This number 18 is on a linear expansion. You want to take apart a couple copper parts held together by brass screws, but the screws are stuck. What should you do? And then I give you the coefficients of linear expansion for copper and brass. So imagine that I have a copper block and I have a brass screw inside of that copper block, and I want to figure out some way to get it out. I want either the brass to get smaller or the copper to get bigger. So what could I do here? Could I heat them both, cool them both, heat the screw, or none of these? Let's see, if I heated them both, which one would get bigger? The brass would get bigger, right? So that wouldn't work, right? If I heated them both. If I cooled them both, but the brass would get smaller by a greater amount. Yeah, so because this has a bigger coefficient, it's going to get either smaller or bigger when you change the temperature. Right, so it looks like B is the right answer. If I heated the screw, that would just make it worse, right? It would get bigger, and D is not right. So B is the right answer. Think about that coefficient of linear expansion. It tells you how much two substances are going to change in size relatively. And if you forget, you can look back at that equation, delta L equals L naught alpha delta T. If alpha is big, delta L will be big. If alpha is small, delta L will be small relative to the other things. Where was I? What's the smallest unit of temperature? What is that? Fahrenheit, right? Because with Fahrenheit, between the freezing and boiling points of water, we have 180 degrees, 32 to 212. But for Celsius, we just have 100 degrees. So it splits it up 180 times, whereas Celsius only splits it up 100 times. So Fahrenheit has the smallest degree. Let's see. Heat flow occurs between two bodies in thermal contact. They differ in what property? If I have heat flow between two objects, how are they different? Nope, not specific heat. Temperature, right. That's the zeroth law, right? That I have heat flow between two objects of different temperature. And remember, thermal equilibrium occurs if I have thermal equilibrium. This occurs when they are at the same temperature. And what that means is when I have thermal equilibrium, say if these are both at 100 degrees Celsius, then I have no energy transfer between them. There's no energy going back and forth between those two objects. It doesn't matter about the specific heat, although we don't actually get into specific heat, not till chapter 11, which we're not doing. But it doesn't matter about the specific heat. I can have two dissimilar objects, a wood block and a metal block together. And if they're the same temperature, you won't have any flow of energy between them. All right, let's see. That's it for chapter 10, or chapter 10. You want to look anything in particular in chapter 10, or we can go back and look at chapter 9 since we have some time. Chapter 9 is all that fluid stuff, density, all that business, density, Pascals, Bernoullis. We did that last week, but I'm going to go over it a little bit. Oh, okay, well, there's a lot in chapter 9, so let's, okay. Okay, so we'll sort of hit all the high spots. So here you have fluid flowing through a pipe. Because of the conservation of matter, V2 is larger than V1. Conservation of matter tells us which of those equations, Bernoulli's or the equation of continuity. That's right, equation of continuity. Bernoulli's, remember, is based on the conservation of energy. Okay, but here, if I have fluid that flows from here to here, it goes faster here because whatever fluid I have in this part of the pipe, I have to squeeze it through this part of the pipe. So it has to go through here faster. And now it says these standpipes, they measure the pressure. So if I have a high pressure, it's going to be up high. If I have a low pressure, the fluid level will be down low. That's a standpipe. It's used to measure pressure. Well, that's the question. So where is the pressure highest? The pressure is highest here, right? Low velocity, high pressure. That doesn't really make any sense, but that's the way it is. All right. If my speed is low, I have high pressure. If my speed is high, I have low pressure. All right. So like when you put your finger over the end of a water hose, what happens to the speed of the water coming out? It goes faster by the equation of continuity. What happens to the pressure of the water coming out? Did it increase or decrease? It gets smaller. Yeah. Doesn't seem like it, right? It seems like, well, it's coming out faster, it has a higher pressure, but the pressure is actually lower. Right. Yeah, okay. Yeah. It doesn't really make sense to me, but I'm glad it does to you. But when it comes faster, it has a lower pressure. All right. And again, we talked about this in the concept test, but like if I have a fluid that's going up a pipe or whatever, and then I have a high velocity fluid that's flowing, what it does, since it has a big velocity, it creates a low pressure. And so what it works to do is it sucks this fluid up this pipe. Right, that's what do we call that? I always forget. Yeah, vacuum. In medical field, a nebulizer? I don't remember. But I'm sorry. So if I have this stream of gas over the top, it's going to suck up this, whatever I have here. Like the chimney problem, yeah. So that's like the chimney problem too. So make sure that you understand Bernoulli's principle in that sense, and then also that you're able to calculate that velocity like we did before. Okay, you'll have some basic density stuff. So here a metal has a density here. I want to know what is the mass of a block that's 4 cubic meters. Again, knowing the equation and knowing what the numbers are to put in. The equations are on your sheet. Be careful though, because on the test I don't give any densities. I might tell you what the object is, but you'll need to go back and look on that equation sheet. So I'm looking for the mass. The mass is equal to the density times the volume. So it's going to be 4,800. 1,200 times 4 kilograms. A is the right answer there. Okay, let's look at this. Archimedes' principle. Remember, Archimedes' principle says that the buoyant force is equal to the weight of the displaced fluid. Every object that's inside a fluid displaces a certain amount of that fluid, and the buoyant force is equal to the weight of that amount of displaced fluid. So that's the density of the fluid times the volume of the object, or the submerged volume of the object, times g. So here, this boat has a volume of 1 cubic meter, and the mass is 500 kilograms, and I want to know what fraction of the boat is submerged in the water. So a couple steps you have to take here. First of all, the I know that the buoyant force has to equal the weight. The reason I know that, if I have a boat floating in the water, I have a weight and I have a buoyant force that's acting on this. In order for it to just be sitting there floating, those two have to be equal. So the buoyant force has to equal the weight, which is 5,000 newtons. So that's one way to know what my buoyant force is. It has to be equal to my weight. So I'd say 5,000 equals the density of the fluid. That's 1,000. That's the density of water. You use a lot of water, so just sort of know the density of water is 1,000, okay? It's on your equation sheet, but times the volume of the object times G, which is 10. So it's going to be 5,000 over 10,000. So the volume of the object is 0.5. But look, I gave the volume up here, so what gives? Like, why didn't I just use this volume? Right, the whole boat is, right, only half of the boat is submerged. So only a half a cubic meter of the boat is submerged, even though it has a total volume of 1 cubic meter. Okay, so that's the answer to the question, is it's only halfway submerged. All right, I could also ask you to what depth is it submerged, in which case, like, let's say that I told you that the boat had an area of, I don't know, 3 square meters. That's the area of the boat. Like if you're looking at the boat from the top, it'll be 3 square meters. You follow what I'm saying? And then I ask you, well, how deep does it sit in the water? Where's the water line? If you look back at the old test, you'll see a question similar to this. So I would say, well, I know that the volume equals to the area times the depth. So I'd say 0.5 equals 3 times d, which is the depth. And so d is 1/6 meter. Solve that for d. 0.5 over 3. Isn't that right? Yeah, 0.5 over 3 is 1/6. Okay? You'll have one or two like that. You have a couple. You do have 2 Archimedes. One is a calculation, and then one is a, you know, like one of those concept test questions from the PowerPoint. It's actually one directly from there. Okay? That clear this? How y'all feeling? Comfortable? Should sort of feel sort of comfortable. I mean, it's nice to feel a little bit uncomfortable, but you should sort of feel comfortable. Yeah. Right. And don't forget chapter 8 too, because that's not an easy chapter. All right. So here we have one very similar to this on the concept test, but on the concept test, the object was floating. So which one's going to be heavier here? Beaker 1, Beaker 2 are both the same. Here, in Beaker 1, you just have water. Beaker 2, you put a steel block inside of it, but you still have water up to the top. Which one's going to be heavier? Or both the same? They're not the same, right? If it was floating, they would be the same. But here, it's not the same. The reason, you're right, the reason that it's not is because the weight of this steel block is bigger than the buoyant force. So the steel block displaces some water, but it's a lot heavier. The steel is heavier than the water it displaces. That came up too in that problem where he said, what if you have this steel block in your boat and you throw it over the side? What happens to the level of the water? Remember that problem? What happened to the level? It went down, the level in the lake. So this is a similar thing. Let me refresh here. So I had this boat. There was a steel block in the bottom of it. And then you take the steel block and you toss it into the water. What happens? What happens is the water level actually drops. The steel block sits on the bottom. And actually the boat now is going to be sort of sitting up higher, but the water level will drop. Because in this case, on the left, the amount of water that's displaced is equal to the weight of the steel. And the steel is really heavy, right? It's very dense. It's denser than water, so it displaces a whole lot more water than its volume. But over here, when you put it into the water, the steel only displaces its volume, which is a lot lighter than the actual weight of the block. Okay? So make sure that you know the ins and outs of Archimedes' principle in that way. All right. Make sure you know how to measure pressures. Here, P, remember, is P naught plus or minus rho GH. That's on your equation sheet. Here, well, here P naught is 0. So this just goes to 0. And in fact, this whole plus minus thing is moot. It's just plus. And I solve there. The barometer is filled with water, so it's 1,000 times 10. times H. Oh, I'm looking for H. And the outer pressure here is 2 atmospheres, so that's 2 times 10 to the 5th. Watch your units, okay? If you ever doubt, just go to SI units. Although that's not always necessary. So it's 200,000 over 10,000, or no, yeah, 10,000. 20 meters. I'm not sure where you got 10. 200,000 over 10,000 is 20. Oh, okay. Yeah, because it was 2 atmospheres. 2 atmospheres. Don't forget, too, this whole plus minus thing, that if I have, this is a barometer, but if I have a manometer is where that P naught is not necessarily 0. We had a problem like this in class, but if I have a pressure over here, P, and then I have a pressure over here, P naught, and then the difference between them is H. P is equal to P naught plus or minus rho GH. Now in this case, is it plus or minus? Is P bigger or smaller than P naught? P is bigger than P naught. Yes, I have to push down on this side to get this side to go up. So this pressure has to be bigger. So P is bigger than P naught. So I'm going to use plus or minus here. I'm going to use the plus. But if it was the other way around, like if this was P naught and this was P, it would be minus. I would have to use a minus there. I'll tell you. Yeah. Honestly, it doesn't really matter what you call P or P naught. I'm just comparing one pressure to another pressure. Yeah. It's just I'm comparing one known pressure to one unknown pressure. Well, usually P is the unknown pressure. Yeah, I think I remember that. Wasn't this one? Was it? It looks like this is the only one. Number 2. Yeah, this is like the one that we just did, except in this one, you have 1 atmosphere instead of 2 atmospheres. It's the one with the. Oh yeah, that is a little confusing, isn't it? Yeah, that's just sort of the way it is. Um, yeah, so here our P naught refers to the pressure that's pushing down, and P is the pressure here. Okay, but over here, P is this pressure, and P naught is this pressure, which is 0. I'm sorry, that's confusing. I don't know, that's just sort of the way it is. You just have to learn to discern them. Yeah, I'm sorry. That's not my doing. That's just sort of the way it is. Okay. Um, let's see. I think we did everything here. Archimedes, Bernoulli's, Archimedes. Oh, Pascal. So you will have one. It'll be something similar to this. Pascal's. I'm not going to make it calculate the area. I'll give you the area straight up. But with Pascal's, remember, Pascal's first of all says that a pressure is felt all the way throughout a fluid. So any change in pressure here is felt everywhere within the fluid. And so P1 is equal to P2, or F over A, in this case, is F over A. So you can solve then, I'm looking for little f here. F then is equal to big F over A times little a. And here you had to solve, like I gave you the diameters, and you had to calculate the areas, pi r squared. You're not going to have to do that on the test. I'll give you the areas straight up. But for a hydraulic, like a jack, or yeah, any hydraulic system uses this. Your car uses this in the brakes. Any kind of, where you have two pistons of dissimilar sizes. All right? I think that's it. If it's okay, I think we'll wrap up there unless there are any other burning questions. Okay, remember, no help session next week. The class, we won't meet in class on Monday. We will meet tomorrow, and we'll sort of wrap up that chapter 10. We're almost done, so we'll use that time to sort of go back some old stuff and just review it. And then on Wednesday, we'll come back together after y'all have been sort of refreshed on the older material and look at it again. But I'll be out all day on Thursday. I'm very sorry for that. I'm going to the zoo. My daughter is their field trip.